7a minus 30? This looks fun. We should do this.
Oh, I will factor all day today. If it means we don't have to do this. All day.
Oh, wow. Hey,
oh my god.
You put 6 drops in a gallon of eye
Okay, 3-6. Okay, summary of curve sketching. Okay, so basically, like I said, we are going to take everything and just kind of take everything we know about graphing and combine it into one. So if I look at 3-6, I'm going to kind of give you kind of things that you want to look for. So the first thing is helpful is domain and range. Range, not so much necessarily. Domain is definitely the important one. So you definitely want to look at it first. Look at your domain. And you definitely want to use it if you see a rational function. Domain is important because it kind of gives you a hint on where your vertical asymptotes will be. If I have a square root, we're thinking we're going to have a specific domain. Now, if it's just a polynomial, we know the domain is negative infinity to infinity, so it's not going to help me a ton. But definitely if you have a rational function, or definitely if you have a square root, you want to look at the domain because that's going to kind of help you down the road to see if you're on the right track. Second thing we want to look for are x and y intercepts. Like we did on 59, plug in 0 for y to find the x-intercept, plug in 0 for x to find the y-intercept, same thing like you've done since algebra. Third one, check for asymptotes, vertical and horizontal. So if I'm looking for vertical asymptotes, we're looking for rational functions, which we kind of did on 59. Where does this graph cannot exist? What x values can this graph not exist at? For horizontal asymptotes, I'm gonna tell you not to worry about the limits necessarily. Use the 3 shortcuts that we talked about yesterday, which has you look at the degree. So I'm going to tell you for the horizontal asymptotes to use those 3 shortcuts. These are already going to take long enough. So I don't think it's necessarily important for you to go through and find the limit every single time for the horizontal asymptote. As long as you know how to do it, that is fine. But when I have you graph it and put it all together, I will let you use those shortcuts. Number 4, symmetry. What section is that in? Someone get out your chapter P notes real quick. Someone have them handy. I know they're in your chapter P somewhere. I think it's chapter P. Who's going to win? Who's going to win? You'll get nothing for doing it, but take your job.
He's getting stressed out. You can't say that.
Hey, you're laughing. Chapter 2.
I was already wrong.
Yeah, symmetry. Very first, P1. Very bottom of the first section. If you need a refresher on symmetry, or if you want to have that out to look at as we go through some, it is on the very first page. When we were all young and naive and knew how to do it. So symmetry is in P1. So plug in negative for your x values, see what you get back. That's the 4th thing. 5th thing, we're going to look for extrema, max or mins, first derivative set equal to 0. You've done it before. We're just putting them all together. What else do I want to put in there? Make sure you find ordered pairs. So if I get a critical point, make sure you plug it in because that's going to help you graph it if I have specific ordered pairs and not just know where the critical points are, because then you can kind of get an idea of where your graph's going to go. Let's see, number 6 is going to be 5. I'm going to put extrema and intervals of increasing and decreasing, which we've done before. So we're you take your critical points, look at your domain, create your intervals, and then check where it's increasing and where it's decreasing. Plug back into first derivative. Let me put a note of that. Plug into first derivative. So you have to keep track of what you're looking for. If I'm looking for a y value, it goes back in the original. If I'm looking for increasing or decreasing, plug it into the first derivative. If I'm looking for concave up or concave down, it goes in the second derivative. So keep track of that. 6, we will do inflection points. And concave up and concave down. So that is second derivative, set equal to 0. And for concavity, plug into second derivative. And then you can you should be able to get a good idea. I hope so, because you have like 20 pieces of information. You should be able to get a good idea of what the graph will look like. I like graphing as I go through. So if I find my intercepts, I like putting them on the graph. If I find my vertical asymptote, I like putting it on the graph. If you want to get all this information and then graph it after all of it, I don't really care. I think it's a little easier to graph it as you go, because it helps you check yourself. Like if you have a vertical asymptote at x equals 2, and then you find out there's a critical point there, then you know you probably did something wrong. So you can check as you go through if you graph after each section. Any questions? Let's do this. Okay, first example. We want to analyze and sketch the graph of the following function. So as I look at this, let's just go through those steps and just see what we have. So the first thing is, I'm going to start up here. You're going to want to write small. First thing is domain and range. So my domain, as I look at it, I do notice that it is a rational function. It is a fraction. So I need to be... So I'm thinking there could possibly be vertical asymptotes. So as I look at this, what will be my domain? Or what x values cannot exist? Yep, because if I plug in a -2 or 2, I get 4 minus 4. I get a 0 on the denominator. So my domain will be -infinity to -2, -2 to 2, and 2 to infinity. And my range, we're not super worried about. This is a little hard to see what my range will be. I'm not really too worried about it right now. If it's a polynomial, you know your range is -infinity to infinity. I'm not really super. Domain is definitely the one that's going to be more helpful. Okay, step 2. Let's look at step 2. Step 2 is finding what? X and Y intercept. So if I'm looking for my x-intercept, I plug 0 in for y. So I'm going to have 0 equals 2 over x squared minus 9 over x squared minus 4. As I start trying to solve this, I can do what? Cancel out the denominator. So I'm going to have 0 equals 2x squared minus 9. Okay, let's go ahead and divide by 2. So that's going to give me 0 equals x squared minus 9. So x is going to be what? Plus or minus 3. So you could factor it if you wanted to. You can just think about what values, if I plug in for x, will give me a positive 9 plus or minus 3. So my x-intercepts are plus or minus 3. So if you want to go ahead and put those on there. 1, 2, 3. 1, 2, 3. I like doing it as we go through. And then my y-intercepts, I plug 0 in where x is. So y equals y-intercepts. So y equals 2, 0 squared minus 9. You don't necessarily have to show this work. I'm just doing it so you can go back and look at it. 0 squared minus 4. So that will give me 2 times the -9, -18 over -4. So 9/2 is my y-intercept. So we'll graph that on your y-axis. 9/2 is really what? 4.5. So 4.5. So I like graphing it as we go, so you can kind of look, kind of double check it as we go. So that's step 1 and 2. You've done that since algebra 2, so that should not be, if that like finding the intercepts is hard for you, then this will be fun. Okay, let's look at 3. Sorry, I apologize if they're hard for you, but it will be. I'm just being real. Okay, 3. We're looking at what? Asymptote. So if I look at my vertical asymptote, I look at what x values I cannot have. You can also kind of refer back to your domain. So my 2 vertical asymptotes will be at, plus or minus 2. So those aren't too terrible to find. If you don't have a rational one, or if you don't have a square root, if you have a polynomial, you won't usually have vertical asymptotes. So plus or minus 2. So negative 2, positive 2. Okay. My horizontal asymptotes, you can look at the limit. Like you can take the limit as x goes to infinity and divide by the highest exponent in the denominator, or use this shortcut. Let's go ahead and look at those 3 shortcuts we talked about yesterday. Look at your degree. So if I look at my degree, the degree of the top and the degree of the bottom are what? The same. If they are the same, then I look at my leading coefficient. So what is the leading coefficient on top? No. 2. Think about distributing. If I would distribute it and put it in standard form, my leading coefficient would be 2. What's my leading coefficient of the bottom? 1. So 2 over 1. Set it as a fraction. So 2. So my horizontal asymptote is at 2. Any questions so far? Next thing we look for is what? Symmetry. So if I look for symmetry, plug in a negative x. You can kind of might be able to look at it. As I plug in a negative x, I notice I only have even exponents with the x. So if I only have even exponents, that tells me what? That I'm always going to get back the same thing. So if I only have even exponents, that means when I plug in a negative x, I will get back positives. So I will get back the same thing. And if I plug in negative x and get back the original, it is symmetric with the, look at the bottom of P1 notes if you need to. Symmetric with the y-axis. So symmetric with y-axis. So not a super huge deal. Like symmetry isn't going to tell you immediately what your graph will look like. It doesn't really give you specific points. But it does kind of tell you, as I'm walking through this and finding things, that I should be symmetric with the y-axis. And just by looking at the graph what I have now, why does it look like it's symmetric with the y-axis? My asymptotes were negative 2 and 2. My point intercepts were negative 3 and 3. It looks like it is symmetric with my y-axis. So like I said, as you go through these steps, you can kind of check yourself. If you graph after each step, you can kind of check yourself as you go through it. Check yourself before you wreck yourself. That's motto for the day. Okay, anyway, 5. Let's look at 5. 5 is what? Extrema. Increasing, decreasing. First derivative set equal to 0, starting with the calculus. So let's look at taking my first derivative and set it equal to 0. So let's go ahead and simplify this. Let's distribute the 2 first before I take the first derivative. 2x squared minus 18 over x squared minus 4. You could have done that at the very beginning. It doesn't really matter. But since I'm taking the first derivative, I want it as simplified as possible before I try to take the first derivative. I'm going to have to do what when I take the first derivative? Quotient rule. Let's see. Low x squared minus 4 d high, which will be 4x, minus high, 2x squared minus 18, d low, which is 2x, all over square of what's below, which is x squared minus 4 squared. Okay, now be careful with this. Let's go ahead. I'm not going to cancel out the denominator until I have it all the way simplified, so that way I don't get confused at what to plug back in to check for increasing, decreasing. So don't lose the denominator yet. Let's simplify the top, and then we will lose the denominator when I try to solve for x. So I'm going to have distribute 4x to the third minus 16x minus 4x to the third plus 36x. Is that right? Yes. Go ahead and keep the bottom part. Otherwise, you might get confused when you plug in to check increasing or decreasing. You might try to plug it into the part that doesn't have a denominator. So this will simplify down to what? 20x over x squared minus 4 squared. So that is my simplified first derivative. So keep your denominator because we need to know my simplified first derivative when I plug it in to check increasing, decreasing. Now let's go ahead and find my critical point. So set it equal to 0. When I set it equal to 0, I really only have to be worried about the 20x, the numerator. And if I solve that for x, x is going to be 0. So that tells me that I have a critical number at 0. Now be careful, that's a critical number, it's not a critical point, so I don't necessarily know what the y value is, so always find an ordered pair for a critical number, find your critical point, because that's going to give you more specifics about the graph. So plug 0 where? If I want to know the ordered pair, I plug 0 into the original. If you ever want to find y, you always plug into the original. So if I plug into the original, I get back, well, let's think about it. We already did the work. If my x value is 0, what do I know my y value is going to be? 9 over 2. I already did the work. This is basically the y-intercept. I already plugged in 0 for x when I did the y-intercept. So that's 9/2. I'll make a side note. Plug into f of x. So I'll just make a side note so you know where that 9/2 comes from. You plug x back into your f of x or your original. So that is my critical point. So that tells me where I'm going to switch concavity. Not concavity, increasing, decreasing. Now as I look at this, it should kind of continue to make sense with your graph. I have a point here, that is my y-intercept, so that is also my critical point. So that is where I'm going to switch from increasing to decreasing. So now that I have a critical point, let's go ahead and check my interval and see what I have where I'm increasing or decreasing at. So if I check my interval, look at your domain. So it's from negative infinity to negative 2. Do I have to plug in a 9/2 there? What do I have to include in my intervals? 0. The 9/2 is a y value. 0 is the x value. So since that's where my critical point is, I have to plug that into the interval with the domain. So my intervals are going to be negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity like we've done before. So you have to take into account the domain and the critical number. So now as I go through and check the increasing, decreasing, I plug into the first derivative. So plug into first derivative. So just making some notes as you go through and look, you know where I'm getting my answers. So look at your simplified first derivative. This is why I kept the denominator there the whole time. So you make sure you plug it into the denominator too. So let's think about this. If I plug in a negative 3, I'm going to get a 1 on top. Negative over what am I always going to get in the bottom? Because I'm always going to square something. So I'm going to have a negative over a positive, so that will give me a, so that's decreasing. Negative 2 to 0. If I plug in a negative 1, I'm going to get a what on top? Negative over positive, so that is also decreasing. 0 to 2, if I plug in a 1, I'm going to get back a positive. Positive over positive, so it's going to be increasing. And if I plug in a 3, I'm going to get back a positive, which makes sense. Usually, not always necessarily, I'm going to switch at a critical point. If it's a weird graph, we might not necessarily switch at my critical number. Usually you will. So now I know where it's increasing and decreasing at. Okay. So now let's go ahead. It's hard to graph that. You can't really graph increasing, decreasing without concavity. So you kind of have to wait to graph until you have the increasing, decreasing, and concavity, and then you can kind of draw your curves. Okay, let's go ahead and look at that was step 5. Step 6 is finding the second derivative. Let me kind of draw. Step 6 is finding the second derivative, critical or inflection points, concavity, all that stuff. So as I look at my second derivative, you want to use the simplified first derivative. So that's another reason why I kept the denominator there till the very end, so that that way when you take the second derivative, you don't just take the numerator, you have to take the denominator with it. So I'm going to have to do the what again? Quotient rule. So we're going to have second derivative equals low x squared minus 4 squared, d high, which is what? 20, minus high, 20x, d low, which is going to be, yeah, so 2x squared minus 4 to the first times chain rule, inside part, which is 2x over low d high minus high d low over square what's below, so x squared minus 4 to the fourth when I square it. Okay, so let's simplify the top. This is what we did the day before yesterday, so Friday. Let's simplify the top, factor out what I can. This is why we spent the time factoring on the study guide last why we took out the factoring stuff so we could practice doing it. So as I look at my two terms on top, what can I factor out? Uh, 20 what? No, because this first term doesn't have an x squared, so I can just take out a. Let's go ahead and do this. We'll do this first. 20. We'll rewrite it first, so it's easier to see. Let's rewrite it first. So the 20 comes out front. I'm going to have what out front for my second one? 22, 40, 80 x squared. There, it's a little easier to see. This is x squared minus 4. I'm going to keep the denominator there. You don't really have to do anything with it, but just keep it there. So now it's easier to see. Now what am I going to factor out? Yeah, before that, I can also take out a what? 20. So 20 x squared minus 4 to the lowest exponent first. And let's see what I have left. I took out a 20, so I'm going to have an x squared minus 4 to the first power, which is just itself, left. And then what am I going to have left from the second one? Minus 4x squared, because I took out a 20. So to get back 80, I need a negative 4x squared. All over x squared minus 4 to the fourth. Okay, let's simplify a little bit. Couple things I can do is what? Yep, so this will be an x squared minus 4 to the third. So I'm going to have 20 negative 3x squared minus 4 over x squared minus 4 to the third. That's my second derivative. Now I want to go through and find the inflection point. So I take my second derivative and do what with it? Set it equal to 0. So if I set it equal to 0, I don't have to be worried about the denominator part. I also don't have to be worried about the what? 20, because I'm going to be dividing by 20. So I'm just going to set it equal to negative 3x squared minus 4. If I try to solve this for x, I'm going to get 4 equals negative 3x squared. Divide by negative 3. What issue do I run into? Square rooting a negative. So if I try to take the square root of a negative, I can't do that. So what does that tell me? I have no inflection points. Yay, all that work for nothing. So just like the one we did on the notes, we had no critical points for the one we did on, not the notes, the homework, 59. Now I have no inflection point. So what does that tell me? If I do not have an inflection point, what does that tell me about the concavity of the graph? It's the same the entire way through. So since I don't have inflection points, it's not going to switch anywhere. So that tells me that through my whole graph, my whole domain, I should either be concaving up the entire time or concaving down the entire time. So let's go ahead and check my intervals to see what I'm doing. Just to double check I'm on the right track. So negative infinity to negative 2, negative 2 to 2, and 2 to infinity. So basically I just have to check my domain because I don't have any inflection points that I have to check, that I have to plug in there or throw in the interval. Any questions so far? Okay, this we are plugging into plug in second derivative, just as a note. So as you go through, I plug that into the second derivative because I'm looking to concavity. So the simplified second derivative is right here. So make sure you pick the right one. If I plug in a negative 3, so I'm always going to get a what in the denominator because I'm going to square, not necessarily because I'm cubing something. So you won't, well, yeah, but I could technically square and get back something smaller than it. So I could still get a negative, so we have to, usually not. But if I plug in a negative 3, I'm going to get a what on the top? 9 negative times 20, negative over positive. So I'm going to get a negative, so that's going to be decreasing. So I'm thinking that I should be decreasing over the entire, is that right? What did I do wrong? Let's see. Okay, so there's no inflection points. Okay, I said that wrong. There's no inflection points. That doesn't necessarily mean that it's going to be the same concavity over the entire graph. So I said that wrong. Because I have those asymptotes, I can technically switch concavity without having an inflection point because I can switch after the asymptotes. Does that make sense? I said that wrong. So just because I don't have an inflection, now if I didn't have any inflection points and I didn't have any asymptotes, then I know it would stay the same the whole time. But since I have those asymptotes, it can still technically switch between the asymptotes without having an inflection point. Sorry, I misspoke on that one. So if I check between negative 2 and 2, if I plug that in, plug in 0, I'm going to get negative over negative, so positive, so that is concave up. So yes, just because there's not an inflection point does not mean it will stay the same. I misspoke on that one. Now if I plug in a positive 3, I will have a negative over positive, so that will be concave down. Now, why did I know that that had to be concave down? Yeah, the symmetry. So the symmetry kind of told you that if it's symmetric at the y, it should be concaving down on that side too. So if I look at graphing this real quick, we are going to have, kind of throw all this stuff together. So start from your lefts, and let's see what I have. From negative infinity to negative 2, I have the point, I have the x-intercept there, so I know it has to go through the x-intercept. From negative infinity to negative 2, I'm going to have decreasing. So negative infinity to negative 2, I am decreasing, and I am concave down. So it has to go through that point, and it's approaching those asymptotes. So I am decreasing, and I also am concaving down. I have kind of a frowny face curve. So I'm decreasing, and I'm concaving down. Now in the middle part, I have my increasing, decreasing is switched. So from negative 2 to 0, I am decreasing, and at 0 to 2, I am increasing. And negative 2 to 2, I am concave up. So decreasing till 0, increasing till 2, and I'm concave up the whole time, which kind of makes sense. And then the last part, from 2 to infinity, I am doing what? Concave down and increasing. So I am increasing, so I'm technically going up. That's kind of hard to see it's increasing. I'm still increasing, and I am concave down, because that would be like a frowny face curve. So that is my graph. Any questions? And that took good times. That one would take a little shorter because you're not going to go through every single step. I was very precise with what I showed, but okay. Any questions? And this is why it's a 2-day lesson. Okay, let's look at the next one. Maybe we'll go through it. No, we're going to. Okay, example 2. So if I look at example 2, analyze and sketch the graph of the following function. Okay, so go through all those steps. First step we are looking at is the domain. Range we're usually not super worried about, so technically it's just the domain. If I look at this one, it is a rational function. My domain will be negative infinity to 4 and 4 to infinity. The range we're not usually that worried about, just FYI. If I look at the next one, which is intercepts, x-intercepts, plug in 0 for y. So 0 equals, I'm really only going to be worried about the top part, x squared minus 6x plus 12. It is a quadratic, so I want to try to do what first? Factor. Are there two numbers that multiply to give me 12 and add to give me negative 6? Oh joy, just to make these a little more fun. This does not factor, so I'm going to do, you could complete the square, I'm going to do quadratic formula because I know it will always work. So let's do quadratic formula because we can, because it's Valentine's Day. So x equals negative b, which is 6, plus or minus b squared, 36, minus 4 times a times c, 1 times 12. I am kind of not going to write this out for you all the way. All over 2 times 1, 2 times a, so 2. So I will have 6 plus or minus the square root of 36 minus 48, which is negative 12. And right there, I see, yeah, square root of a negative. So we would technically have an imaginary number, but since we're graphing it, imaginary numbers don't show up on the graph, so I don't really care about them. So we're just going to say no x-intercepts. So technically, yes, you would have an imaginary, but they don't show up on the normal graph, so I'm not going to worry about them. My y-intercept, if I'm looking for my y-intercept, plug in 0 for x. You don't necessarily have to show this step, but if I plug in 0 for x, I'm going to get back 12 over negative 4 or negative 3. So my y-intercept is negative 3. I do not have any x-intercepts. Questions so far? Good. Okay, step 3 is looking at my asymptotes. Vertical asymptote, which is probably the easiest to find, is going to be at what? X equals 4. What x values cannot exist? We're going to be 0 in the denominator. X equals 4. Okay. Horizontal asymptotes. Use those 3 shortcuts. Look at your degree. The degree of the what is compared to the degree of the bottom. The top is bigger. If the top is bigger, it doesn't exist. However, we will have a slant asymptote. We could have a slant asymptote. So we're like throwing all these weird things in on this one. Like I said, I want to do harder ones with you. So I want to do ones where you have a slant asymptote and where you have to use Pythagorean theorem. So if you get to it on the homework, you are somewhat familiar with it. So since the top is bigger, technically it would be does not exist. However, we need to check for a slant asymptote. How we check for a slant asymptote, I will be impressed if anybody remembers. For the candy Blake gave me? No. Okay. You do long division, and your non-remainder is what your slant asymptote is. You'll be fine. I would like to think I feel bad for you, but I don't. Okay, long division. X times what? What times x gives me x squared? X. So I put that on top. X times x is x squared. Multiply through. X times negative 4, negative 4x. Subtract it. So switch the sign. Minus plus. So I'm left with negative 2x plus 12. What times x gives me negative 2? Or negative 4? Sorry. What times what times x gives me negative 2x? Negative 2. Sorry. I don't know why. Negative 2. So multiply through negative 2x plus 8. Subtract. So change the signs. So it's going to be a 4. So I will have a remainder of 4. So that always goes over your, I always get confused. Number up front. Divisor or dividend? I don't know, it doesn't really matter. So plus 4 over x minus 4. It goes over whatever's up. I cannot remember that for the life of me. So if you have a slant asymptote, do long division. Whatever is your non-remainder part is your equation for your slant asymptote. So your equation is just y equals x minus 2. That is the equation for your slant asymptote. It's a line, graphing it. It's fine. I get it, long division is annoying, but you can graph this line. So negative 2 is your y-intercept, up 1, right 1, up 1, right 1. So I have a slant asymptote, right? Something like that. Okay. Any questions? So as I'm looking at my graph, this still has to be a function. So I noticed that I have a point down here, like on this bottom triangle part. So because this has to still be a function and keep the vertical line test, I'm thinking there's going to be nothing up here. I'm going to have something exist down here. Because if I had something in both places, it would not pass the vertical line test. So just kind of things to think about from what you already know, because it has to stay a function. So I have my vertical asymptote. I have my horizontal asymptote. Step 4 is to cry. No, just kidding. Step 4 is symmetry. So let's plug in a negative x and see what I get back. Negative x squared minus 6 times negative x plus 12 over negative x minus 4. I notice not all of my exponents are negative or even, so I can't necessarily just kind of think about it. That will be a positive x squared plus 6x plus 12 over negative x minus 4. Do I get back the original? No. Will taking out a negative 1 get me back to the original? No. So there is no symmetry. So sometimes there'll be symmetry, sometimes there won't. Symmetry isn't a huge deal, but it helps you kind of visually think about the graph as you work through it if you're on the right track. Okay. Everyone's favorite part now. Step 5. Let's turn the calculus. Step 5. Extrema, max or min, critical points, increasing, decreasing. That is all the first derivative. So let's go ahead and look at taking the first derivative. If I'm taking the first derivative of this, we are going to have to use the, of course. So if I look at doing the quotient rule, what did I do? Now, quotient rule. Well, think about it. We kind of talked about it yesterday. I could use the quotient rule, or I could use, what else could I use? No. What's the same thing as this? What did I rewrite? What function is the same as this function? This is division, so what function is literally the same as this divided by this? This. Yeah. I can use this because it's literally the same equation. I just actually divided them out. So this is literally the same function, just actually divided out. We never actually do this because it's annoying to do long division. But since I had to do it anyway, you can just use this. So if that is my original, it's going to be a little easier because I kind of just have a polynomial form. So that is literally the same function. I just actually divided it out, which we never do because we usually never use long division. But since I have it done anyway because of the slight asymptote, we can just use that to take the first derivative. So now as I take the first derivative of this, it's a little easier. First derivative of x, 1. First derivative of negative 2, 0. Now I still need to use the quotient rule, but this is an easy quotient rule. So plus low d high, which is 0. So that takes out that whole chunk. Minus high d low, which is just 1, all over x minus 4 squared. So it's kind of a shortcut if you use your quotient from the long division, which is literally the same function, just actually divided out. Makes it a little easier. So we're going to have y prime equals 1 plus, actually minus, that's annoying me, but whatever, negative 4 over x minus 4 squared, because the 0 cancels out the x minus 4 part. I have a negative 4, I have an x minus 4 squared. Let's simplify this. If I simplify this, let's combine it into 1. So since I have two fractions, let's combine it into 1 real quick. It'll be easier to look at. So I'm going to have to multiply my top fraction by, do I want to do that? I could. Let's just leave it like this. Let's think about it. If I set it equal to 0, that's going to, I think that might make more work. So I have 1 minus 4 over x minus 4 squared. Let's think about setting it equal to 0. If I set it equal to 0, okay, I could technically subtract 1, divide by negative. So this is the same as 1 equals 4 over x minus 4 squared. So what I'm doing is I'm just kind of moving the 1 over and dividing by the negative, so it's easier to literally think about this. So what x value, if I plug in for x, will give me a 4, or give me a 0. So if this is a 4 on top, what do I need on the bottom that will give me a 4 over 4? So if I want this fraction to be equal to 1, I want to get a 4 on top over a 4. So what x value, if I plug in, will allow me to get a 4 in the denominator? So what minus 2 squared will give me a 4? So basically, what minus 4 will give me a 2 or a negative 2? Does that make sense? 6 or 2. So you could get common denominators, but then that would force you to FOIL on the top and combine. That would work. Or you can just kind of think about it. I want both sides to be equal. So if I plug in a 6, I get 6 minus 4, 2 squared, 4 over 4, which is 1. If I plug in a 2, 2 minus 4 is negative 2 squared is a 4, 4 over 4 is a 1. So you can either get common denominators, go through the foiling, which you would get eventually to the right answer, or you can just kind of think about it. Okay, so those are my critical numbers. And let's go ahead and look at let's look at my actual points. So if I plug in the original, because you always want to find the actual points, because that'll help you get more specific graphs when you're graphing it. If I plug in a 6 to the original, let's see what I get. Let's kind of think about it. 36 minus plus 12 is 12 over 2. So 6. So 6, 6 is 1 critical point. If I plug in a 2 to the original, I'm going to have 4 minus 12, which is negative 8, plus 12. 4 over negative 2, which is, what was it? Negative 2. 4 negative 2. No, 2 negative 2. 2 negative 2. Sorry, 2 negative 2. Is that right?
Yeah.
Yeah. Okay. Yeah, we got that. I got negative 1 for some reason, but I think I did it wrong. You got negative. Did anyone else get negative 2? Okay, we'll say it's negative 2. Okay, those are my critical points. So that is where I'm going to probably switch increasing, decreasing. So as I write my interval, I have my domain, negative infinity to 4. Now be careful, I have to take into account my critical points. So that's going to be negative infinity to 2, 2 to 4, 4 to 6, and 6 to infinity. So I have to take into account my domain, which is negative 0 to 4, negative infinity to 4, 4 to infinity, and then take into account the critical points as well. So I have to take into account 2 and 6. Questions on that? Now let's plug it into the first derivative. I would use this one, the simplified one. So if I plug in a 0 for the first one, do I get back a positive or a negative? If I plug in a 0, negative 4 squared is, so 1 minus 1/4 is a positive, so that is increasing. If I plug in a 3, 3 minus 4 is negative 1 squared, so negative 4 over 1. 1 minus 4, negative, so decreasing. If I plug in a 5 to here to this one, that will be 1 squared, so negative 4 over 1. 1 minus 4 is decreasing again. And if I plug in a 7, 3 squared, which is 9, so 1 minus 4/9 is a positive. 1 minus the fraction is always a positive, so that's also increasing. Okay, any questions on that? Okay, let's look at step 6, finally. Let's look at the inflection points, concavity, second derivative set equal to 0. If I look at the second derivative, use this one, the simplified one. So if I look at it, what's the derivative of 1? Derivative of 1? 0. So you can put it 0, it's gone. And then I'm going to have to go through and do the quotient rule for my fraction part. So low x squared minus 4 squared, d high, which is what? What's the derivative of 4? 0. Minus high, which is already a negative 4. High d low, which is chain rule, so it's going to be 2x minus 4 to the first times the derivative of the inside, which is just 1, all over square of what's below. So So x minus 4 to the 4th. Any questions on that? Let's go through, simplify it. That 0 I don't really need to worry about. X minus 4 squared times 0 is gone. So I'm just going to have this part up here. So if I take an 8 and distribute it through, that's going to be 8x minus 32 over x minus 4 to the 4th. Anybody see what I can do? Do what? Yeah, take out an 8. Yeah, you're right. Which you could have not factored it, not foiled, or not distributed it, and you would have seen it. But yeah, you can take out an 8. So now if I simplify, now be careful because I'm factoring it out. So why will there not be a whole at 4? Because usually when I factor and cancel stuff out, that gives me a whole. Why would there not be a whole at 4? Because there's an asymptote plus this is the second derivative. If you did it with the original, that's fine. This one you did with the second derivative, so you don't need to worry about it. Okay, so let's go ahead. Those are gonna cancel, so you're gonna have 8 over x minus 4 to the 3rd. If I set it equal to 0, 0 equals 8. So once again, I have no inflection point. Which, be careful, I misspoke last time. Doesn't necessarily mean it's going to be the same over the entire part because I have the asymptote. So it still could switch between the two asymptotes. But that does tell me what is the only interval I have to check concavity. The domain. So negative infinity to 4 and 4 to infinity. So I don't have to plug in any points to check between just the domain. So negative infinity to 4, if I plug it into the simplified second derivative, if I plug in a 0, I get back negative. So that is concave down. And if I plug in a positive 5, 8 over 1 cubed is positive concave up. So as I go through my graph, check your interval. We have let's go ahead and plot my inflection points real quick. My inflection points are 2, negative 2, and 6, 6. Okay, I like plotting the inflection points. That kind of gives you a hint as where your graph should kind of look at. So it tells you what parts I should be at. I have a point up here on this top triangle, so that tells me to keep it a function and pass the vertical line test. There should be nothing down here. So if I graph this real quick, from negative infinity to 2, I am increasing and concave down. So it should be a kind of approaching the asymptotes. I am increasing, I am concaving down. I'm approaching the asymptotes. From 2 to 4, I am decreasing, but I'm still concaving down, so I still have the frowny face, which kind of makes sense with the asymptotes, because you approach the asymptote. And then from 4 to 6, I am decreasing and concave up. Decreasing, I have the happy smiley face, because it took us 25 minutes to do this. And then I'm still concaving up, and I'm increasing from 6 to infinity, so something like that. Okay. Questions? Okay. So look at your homework real quick. And